This is Unit 6, Section 6.1, starting our new unit off on sampling distributions. So as we move into the second part of our year, really, we're going to be looking at something called inference. And so this is going to lay a foundation for what's going to be going on in Unit 7, 8, 9, 10, and kind of the rest of the year. And so we'll look at kind of some basics first, and then we'll go into proportions and means. And so our first idea is just starting to use estimating a sampling distribution using a simulation. And so we'll start looking at some definitions as well as looking at what is the difference between a sample and a sampling distribution. And so that's going to be our key vocab today. All right, so 6.1 sampling distributions, we have parameter versus statistic. So we've been pretty good about defining as, we have a mean, we have a sample mean. So now we're going to start looking at this idea. And so we're studying statistics, but what we're trying to infer about is a parameter. And so a parameter is a number that describes some characteristic of a population. Okay, parameter, population, P with P. So this value is usually unknown, and this is what we're trying to estimate with our statistic. All right, so if I had P, this would be my parameter. If I had mu, this would be my parameter. Sigma, what else could we have? So this would be a proportion, a mean, a standard deviation, and some of them, they don't differ. When we talk about median, we would just have to say the population median. Because what we're going to use next is our statistic. And so our statistic is a number that describes a characteristic of a sample. So again, statistic, sample. This value is known. We've collected this data, and it's used to estimate the parameter. And so we are going to have some proportion parameter that we're trying to maybe figure out. What is the true proportion of AP students that have a 3 or better GPA? Well, we can start estimating that with a sample. I might not have access to all AP students, but I have access to a well-organized sample here. And so I could use p hat to predict what this p is. Maybe I'm looking at a mean. I could use a sample mean to predict the parameter. Maybe I have a standard deviation from my sample. I could use that to predict here. And again, median doesn't have a difference here. We would just have to use context to know if we're talking about the population or a sample statistic here. All right, so let's look at this, just kind of telling the difference between, am I talking about the big idea parameter about a population, or am I talking about something we've collected data from a sample statistic? So in each example, it says each bold-faced number in questions 1 and 2 is the value of either a parameter or a statistic. In each case, state which it is and use the appropriate notation to describe the number. So it says on Tuesday, the bottles of Arizona iced tea were filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. All right, so we want to know what's the parameter and what's the statistic. All right, so our parameter, this is looking at the average. So we have an average here and an average here. So when it says in the plant, these are supposed to contain 20 ounces, that's our parameter. On average, the parameter should be 20 ounces. The statistic is what we collected. He sampled 50 bottles. Those bottles contained an average, and this is where we would use X bar. This is not talking about the entire plant. This is just talking about those 50 bottles that he's sampling. So this one is not the exact same. And so as we continue in our year, we're going to start looking at, okay, is that difference significant? Or is that just because it happened to have a little bit smaller on average? Or is this something that they should halt control and they should say, halt production, we are going to fix this. Our machine is not giving everybody enough Arizona iced tea. That's what we're going to start analyzing next semester. All right, so on number 2, on a New York flight, 8%, or I'm sorry, New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the TSA, 10% of passengers at this airport are chosen for random screening. So again, we have a parameter versus a statistic. And so again, this is where we're using our statistic to estimate the parameter. This is typically unknown or set by a machine or estimated there. So in this case, our parameter, we have 2% here. So we're going to have a P hat. I like that they call that P hat because it's really P with a hat on it. And then we have our statistic P. So our parameter, which is the one that is bigger, the big idea overall, that's what we're looking at as the Transportation Security Administration. The TSA is telling us 10% of the passengers. So our parameter is 10%. This is what we're trying to get to. However, we had only 8% in our sample of 125 passengers that were selected. So again, just like we're going to do with means, we're going to look at proportions in the same way and say, okay, well, we were expecting 10%. That's what they say are being chosen for that random screening, and we only had 8%. Does that mean they're really not following through? Like maybe that airplane or airport is not doing what the TSA recommends as far as being randomly screened? Is that a significant difference from what they have claimed at 10%? That's where we're moving toward. So it's going to be important to be able to tell the difference between a parameter and a statistic. In our next example, it says identify the population, the parameter, the sample, and the statistic. So we want 4 things now. All right, so I just kind of numbered them up here. And so our example says a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates Q3 to equal 56 inches. Can we find these 4 things? So the first thing we're looking for is the population. This is going to be all 10-year-old boys. That's the big idea who we're studying here, which means our sample, okay, we didn't look at all 10-year-old boys. That would be an impossible task to organize all 10-year-old boys and find their heights. So they took a sample. That's going to be the heights of 50 10-year-old boys. So again, our population is always the big idea, 50. Our sample is what we're taking from that population. All right, so parameter versus our statistic. We're interested in the heights of all 10-year-old boys, and we sampled from 50 10-year-old boys. So the pediatrician is trying to find the 75th percentile. And so when we look at the parameter, this is going to be the 75th percentile. So I could say that's quartile 3, but that's what we don't know. We don't actually know the parameter because we aren't able to access the heights of all 10-year-old boys. So when we had 50 10-year-old boys, we could estimate the quartile 3, the 75th percentile, to be 56 inches. So this would be our best guess about all 10-year-old boys, but it's the data that we have sampled from those 50 10-year-old boys. So again, I have labeled them up here so that I have corresponding them here. And then we'll go to the next one. All right, so on the next one, it says a Pew Research Center poll asked 1,102 12 to 17-year-olds in the U.S. if they have a cell phone. Of the respondents, 71% said yes. All right, so the first thing we're looking for is population versus sample. And so the population is going to be 12 to 17-year-olds. And I'm going to say in the U.S. because they've specified in the United States. And then the sample, they asked 1,102 12 to 17-year-olds in US. So they're hoping that this group is a representative sample from this population. And so what we're trying to estimate is the proportion of those students or those 12 to 17-year-olds that have a cell phone. So our parameter is unknown. We don't actually have the data for every single 12 to 17-year-old. We have the data for a p hat, which is going to predict the amount here. So our p hat would predict the amount to be 71%. So these two things go together, our sample of 12-year-olds in the United States with their sample proportion, and the parameter goes with the population. Our unknown parameter, we're not sure exactly what this is, goes with the population here. It's okay to have an unknown parameter. It would not be okay to collect all our data and go, well, I still don't have a number. Well, that's on us. That's the data collection part. So when we start taking our samples over and over again, we start to get a distribution here. And this is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So this would mean if I had all of these students, okay, and if I looked for a sampling distribution, I would look at maybe their GPA. And so if each one of these dots represents a student and I'm looking for a sample size of 2, I could look at these 2 students and find their average. So this would give me an X bar. I could look at these 2 students and this would find me an X bar. I could look at these 2 students and that would find me an X bar. I could look at these 2 students. And again, I'm going to take the distribution of values taken by the statistic in all possible samples. So not only these, but I would also have to go this way and this way and this way and every single possibility with that one. Again, I have way too many dots because this would be a terrible thing to do by hand. And so what this is going to do is it's going to take all of these samples. And once I've taken all of these samples, now we start to get a sampling distribution. And so what it ends up doing is it takes our data about GPAs and finds an average of all the averages of our samples. This is really good practice because that's that idea of that replication that we talked about in experimental design that says if we were to sample over and over and over and over again, we would get more reliable results. So in this case, a sampling distribution is an attempt to find all the possible samples in the same size from that same population. And so we would have, I don't even have a terrible number of dots here, but I have enough that this would be overwhelming to find every single possible combination of 2. But it would give me a really good idea about the GPAs of all my students here. And so one of the things that we want to start thinking about is the variability of our statistics. So when I look at this, maybe this is the smartest person with maybe the not so smart person. I don't know what not so smart putting in there. This average might have a lot of variability. But then when I put it with the second smartest person here, right, this one would not have as much variability as the first one did. This one's going to have a large spread. This one's going to be pretty short. And so when we start looking at the variability or the kind of difference in all our statistics, the amount of spread in a sampling distribution is determined by the size of the random sample. And so if I change this to a sample of 12, well, now I'm going to be looking at a lot less variability because if I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here. All right, if I got 12 in my sample, there's just not going to be as much variation inside of my 12 because even if I have the third smartest person and the second dumbest person, that's not very nice, lowest GPA, I still have all these other GPA people that will kind of lower that difference. It won't make it seem so extreme as this sample of 2 with the smartest and the not so smartest person here. All right, so sampling distribution, all the possible samples in the same size from that same population. Variability of the statistics, it's determined by the size of the sample. Larger samples reduces variability. That is always a good thing. All right, so in our example, it says a father has 4 sons with heights 68, 71, 72, 75 inches. Determine the sampling distribution of the sample mean height x for the samples of n equals 2. Okay, so this would be our samples. And again, I'm picking a very small set of only 4 because like we looked at here, my sample of 1, 2, 3, 4, 5, 6, this was a lot of people, okay? And even my samples of 2, it was hard to find all those combinations. When I'm looking for my samples of 2 here, I'm going to have 68 with 71. That's going to be first son and second son. I'm going to have 68 with 72. First son, third son. 68 with 75. First son, fourth son. And again, I don't know the birth order. They've just put it in order from heights. Maybe this was first to second, third, fourth. I don't know the birth order. But I'm going to find every single possible combination. And so I'm just writing those out. And I'm kind of staying in order so I can stay organized here. And so again, I've gone 68 with 71, 72, 75, 71 with 72 and 75, and 72 with 75. That should be all the possible combinations. It says determine the sampling distribution of the sample mean. So for each one of my samples, I want to find the average. So I'm going to add these together, divide by my 2 in my sample. 68 plus 71, I get 69.5. 68 plus 72 divided by 2. 68 plus 75 divided by 2. 71 plus 72 divided by 2. And keep going. All right. So now these are all my little samples. I've just taken 2 sons and found their height. And so when I look at this, this is my sampling distribution. So I have taken on these values here. I've taken every single possible combination of 2 from the same population here and found the average of each one of those things. So we could have, because we have access to that entire population, we could have found the actual mean by taking the 68 plus 71 plus 72 plus 75 and divided by that 4. And when we do that, we get 71.5. So we know that the average of this is 71.5 inches. That his sons have on average their height is 71.5. He has sons that are shorter, sons that are taller, but on average his sons are about 71.5. This is the really cool thing. Okay, again, we're kind of stretching our brains here because this is a very small sample size from a very small population. If I took the average, okay, you ready for this notation? Of all the averages. Okay, so this is average of the averages. Okay, we use the mu because this is the population. This is all the possible mu or x bars that we could have. And so if I added the 69.5 plus the 70 plus the 71.5 plus the 71.5 plus 73, and the last one 73.5, and divided by the 1, 2, 3, 4, 5, 6 that I have here. When I put this in my calculator, I get the exact same number that we had here. It doesn't seem like such a big idea, but statistically, this is a great thing that's happening. Because if I didn't have access, I could still start to estimate by taking samples and samples and samples and samples and samples. And overall, the distribution is going to start to approach the true average. So again, when we start thinking about these unknown parameters, okay, I might not have access to all the 12 to 17-year-olds in the US at one point to be able to ask them if they have a cell phone. But if I can sample over and over and over again, I'm going to start to get this distribution where, okay, my first sample was at 0.71. My second sample was at 0.7. Okay, I'm going to start to get a distribution of all these samples, and it's going to start to become approximately normal, and I'll start to see the true average or the true proportion in this case. So again, I'm trying to get us to think of where we're going in the next couple units while also trying to introduce this idea that it is a big idea that if we sample over and over and over again, we can start to infer about the population. That's what statistics is all about. So I get a little excited about it. All right. So this is a big thing. We sampled and sampled and sampled, and really we were able to find all of them. And this number is the exact same when we're able to do it with each. All right, so here's our next example. It says Mars Incorporated says that the mix of colors in its M&Ms is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. They are not evenly distributed. People like blue more than they like brown, so they have more blues in it. Graph the population distribution. Okay, so this is where we're looking at a bar graph because these are colors. So I have blue, I have orange, I'm giving myself more room there, green, I have yellow, I have red, and brown. All right, so when I look at that, I'm looking to go up to a max of 24, so maybe I'll count by fives. 5, 10, 15, 20, 25. And I'm counting by percents here. And so my graph, these bars should not touch because these are categorical, so it's just what percent fall into it. So I have blue, orange is at 20, green is at 16, 15, 16. A little bit lower for yellow, but hardly. Red, same thing, hardly. And same for brown. All right, so it's kind of this distribution, and it looks like it's skewed, but keep in mind, we don't have skew when it comes to bar graphs because I could have put these in any other order I wanted to. So we wouldn't describe the distribution. We would just look and start to see hey, I recognize that blue has the most and red and brown have about the same. Yellow isn't far behind. We can make observations about that as far as the values that it's taking, but we can't talk about socks here. All right, so now imagine taking an SRS of 50. All right, so this is the claimed population. The individuals are the M&Ms. The variable we're interested in is the color. The parameter that we're trying to measure, okay, so we're interested in finding the proportion of orange. So we're looking for the proportion, so P, and I'm just going to use a subscript of orange. But this is what's been claimed by Mars Incorporated. So they're saying this is what it should look like. Well, are they keeping true to what they're claiming on their website? So if we imagine, now we're going to take a sample and we have blue, orange, green, yellow, red, and brown. Okay, so if we still have this, can we imagine how many we have here? All right, my handwriting is getting uglier here. So I'm going to look at a count. So I have 50 total M&Ms in my bag over here, and I want to try to think, what did we get here? All right, so here's my p hats, okay, and this is going to be what proportion did you imagine for orange? So if I was going to imagine, maybe I pick my first M&M and it's orange. I pick my second one and it's green. Okay, I'm going to have some sort of count here. And I don't want to do this for you because it should be different for everybody. So pretend you have 50 M&Ms. What's the distribution? Does it match this exactly? Is it all blue? Okay, I mean, what proportion did you get? Is it all orange? Maybe you just had orange and yellow and you didn't know you even got Reese's Pieces. Okay, don't imagine that. We are in a good SRS of 50 M&Ms. But imagine what yours would look like. And then take that proportion. How many imaginary oranges did you get out of 50? And what decimal do you get there? So one of the things that we're starting to look at is this is the population. This is one sample. And again, this is kind of imagining it, so we don't have M&Ms right in front of us. So the third idea is if we have a population and we have one sample, which of the following graphs could be the approximate sampling distribution of the statistic? All right, so if we look at this, this is a frequency and this is the color. Okay, so right now, this would probably be a sample. Maybe the population, but it's a count, right? So this is just saying there's 18 blue. And so I'm saying this is a sample just because it is, it's not giving us an overall population idea. And I know just based on how many M&Ms I've had that there's more than 18 M&Ms in the world that are blue. So I'm guessing this is just a sample. Okay, so we're looking for the sampling distribution. So sampling means taking a sample over and over and over and over and over again. So that's why I wanted us to imagine this. So imagine that now you have a p hat. So you imagined your number, and again, now this is starting to graph a p hat. Where would yours fall? Did you say it was 40% here or 40% here? So what seems reasonable about our sampling distribution? Putting this together with the idea that our sampling distribution should center around the population. Okay, so the population, what they've claimed for orange M&Ms is that it should be around 20%. So as I start to look, if I've sampled from a true distribution and I sample over and over and over again, the center should start to get around 20%. That's this one compared to this one. This is not likely the sampling distribution. If it started to do this, like if I took your sample, imagine, and somebody else's, and we plotted this many samples here where each one of those is a different one, it should start to center around what's been claimed by the population. If it doesn't, we have some serious doubt about their distribution here. So this one's likely. It has the correct center and is a collection of p hats. So each one of these dots could represent our sample of 50 M&Ms that we took here and said, okay, how many orange are there? Well, this is 8 out of however many are in this one. So I would plot my point here. I don't know how many it actually is, but I just took this over and over and over again, and each one of those represents its own sample. It wasn't a complete sampling distribution because unlike the heights of the 4 men, we're not able to get every single combination of 50 M&Ms, but we can get enough that we start to see a trend happening, maybe becoming approximately normal. Woohoo! So our big idea today, what are the differences between the distribution of a population, the distribution of a sample, and the sampling distribution. Okay, the population is usually the claimed idea, or it's from a known population from previous data. The distribution of the sample is one sample taken from this population and collecting it about one piece of information. The sampling distribution of a sampling statistic, or of a sample statistic, this is going to be sampling over and over and over, really going into how many samples do we have here and what are the trends we're starting to see with our sampling over and over and over and over and over. It'll start to take on a trend like this. Hey, if I had a distribution of M&Ms that started to look like this, I believe the company. Yeah, I had a couple that had a lot of oranges. I had a couple that didn't have several oranges. But overall, my samples are supporting that 20% claim. If I was getting a sample in like this, I would start to doubt Mars Incorporated and what they've claimed as their distribution. The population is typically what's claimed or what's known, okay? Or I'm sorry, unknown. The distribution of the sample is what we collect, and the sampling distribution is samples over and over and over and over and over again. All right, let me know if you have any questions over kind of our introduction to sampling distribution.